Thank you very much for introductions. My name is Keita Kanno, manager of the research team at QunaSys. Thank you very much for this opportunity and for organizers and all the audience. Thank you very much for coming. And today I would like to introduce our company's research and development and our efforts to build an ecosystem. Our mission is to maximize the potential of quantum computers and realize industrial application as soon as possible. Chemical computation is expected to be the first industrial application of such quantum computers. In chemical calculations, quantum superpositions, which are the strong point of quantum computers, can be used in the most natural way. The quantum computer can use quantum superposition in the most natural way, which is a strong point. And it has already been shown that the ground state energy of molecules can be efficiently obtained. For large molecules, if a quantum computer with error collection capability is commercial. And therefore, we focus on the chemical computation on quantum computers and conduct algorithms research and software development funded in 2018. And the company has about 30 employees and interns, and is based in Tokyo, but also works with the employees throughout Japan and in Europe. Today, I would like to introduce the algorithm research and cloud service, and this is our products, and the research community building. From these three aspects, I would like to discuss. And first of all, expand the potential of QC. Through joint research with other companies and universities, and we have studied algorithms that exploit the potential of quantum computers and have published 29 papers to date, which I would like to discuss about it some. And this morning, there was a session about it. A VQE, variational quantum eigensolver. This is one of the things. And the VQE is a quantum algorithm that finds the ground state of a molecule and other molecules. The ground state and its energy can be approximately by paralleling, and that state with the parameter theta, and searching for the theta with the minimum energy. The quantum calculator handles the energy calculation, which is difficult in the classic case. Well, the classical calculator takes care of updating theta. The energy calculation itself can be performed in the short circuit, thus avoiding that accumulation of noise. There will be no accumulation of the noise. So even though with the RISC device with the noise, it can be executed, and therefore we're focusing on this, and there is the research going on. We have contributed to the expansion of the application of VQE through our algorithm research and development to date, and I would like to introduce some of them. Molecular dynamics calculations, which track the motion of molecules, are important in the analysis of chemical reactions in an accurate manner. We have developed a new method to accurately calculate the force and applies to atoms in molecules. This method can be widely applied to structure optimization and vibrational frequency analysis. And outlet and solar batteries and such like a photochemistry is important. The development of the wide range of the products, including OLEDs and solar cells. And excited to say it are important for the interaction between lights and molecules. And we have proposed a method to calculate excited state using VQE, we have also proposed a new method to calculate important physical quantities such as transition probabilities using that excited status in the joint paper with the IBM and Mitsubishi Chemical. And not just the molecular, but the accurate band calculations for the solid state materials are important in various fields such as semiconductor development. In our joint research as well, we have extended VQE to periodic systems and developed a method to perform band calculations using VQE. In this way, VQE has been expanding its application, and this was the scope of the research. And for practical applications, it is of course necessary to reduce the noise level of the NISQ devices. Before that, there is also a problem to solve at algorithm. And in each step, energy calculation requires a long time because what is it have to run the same circuit for the many shots and average them, which requires a large number of the shots to reduce errors. It is known that VQE searches for theta and gradually lowers its energy. But this search also requires a large number of steps. An increase in the number of shots causes an increase in the computation time per step, and increase in the numbers of the steps causes an increase in overall computation time. So we can currently working on the research developed to solve these problems so that NISQ devices can be used in real-world chemistry problems. There's some examples. The computation-based sampling method proposed last year paper takes advantage of the fact that the electric state of the molecules are biased to the particular configuration. When tried on several molecules, our proposed method, shown in red, and has the smaller sampling error than the existing popular method, and the blue triangle, and compared performance to the green method, and which requires more complex circuitry. This is expected to reduce the computation time at each step. And the quantum selective CI method, for which we are currently preparing a paper, it is a method of obtaining more accurate and reliable results by processing quantum results such as VQE with the classical calculations. That reduces the required accuracy for VQE, which in turn reduce computation time. In an experiment using 8 qubits of actual INQ equipment with existing method in green had a very large error. Proposed method QSCI gradually become more accurate as a classical cost was increased. And in 5 trials that you see here, and this is better one, the orange one. This is a classical CISD method. It's achieved better, exceeding the classical CISD method, using the same classical cost as read in some cases. So this is very promising, and using that 8 qubits. This is totally different from the VQE. And we made an announcement. And this is a new method to simulate the time evolution of chemical systems on the quantum computer. By compiling on a classical computer, it is now possible to simulate time evolution in very short circuits. And with the large noise disk devices, the time for the computation is going to be enough. And tomorrow, lead researcher Nakagawa will talk about this tomorrow. So please listen to his presentation tomorrow. And this is already active in collaborative research, and it's been prepared for Python open source libraries as well to accelerate this. And from the chemicals down to the circuit levels, it covers. And in the joint research, we implement the new algorithm, and we can use this. And you will be able to use this. And as an open source library, we're preparing to disclose, to be public. And for any device, and you'll be able to use it. And there's the platform agnostics, and also the simple, modular, extensible with the well-defined layers, and fast and efficient. And those are the characteristics. So when it is released, and in the case, please use this and please attend this research. And I've been discussing about the research bit here. And from here, I would like to discuss about our products, and that is the cloud service, Conway. And Conway, and this is a cloud service, and over 3 million of the computation has been run. And ChemE, in one word, on quantum computers and chemical computation is provided. And this is also cloud services. And you don't need to know the details of the quantum algorithm, but still you'll be able to experience the computation of the quantum. And specifically, ChemE takes a chemistry input data and converts it into quantum circuit according to the quantum algorithm, executes it further, and returns to the result to the user as output, such as like a simulator. And simulator, and then also the real machines, you'll be able to test it. And the ChemE will just switch over to. And for the user, you would just rewrite the one line of the job. And this is in a seamless manner, this calculation can be run. And ChemE, it also solves the many of the problems, but with the external libraries, and you'll be able to solve many of the wide variety of the problems. So in a casual manner and simple manner, you'll be able to do the chemical computations with the quantum computing. However, this is more sophisticated ones, which I would like to introduce. And this is with the Mitsubishi Chemical joint research, and using ChemE. And this was a research for the photochemical reactions, and sometimes it fails to describe. And the new algorithm to solve this we have developed, and in order to accelerate the verifications, and before putting onto the paper, we have implemented in ChemE, and using ChemE in the joint searches, and we reach to the publication of the paper afterwards. And this is the paper by Toyota Center R&D Labs introduces the result of study of the effect of the size of the penalty term in the algorithm called the VOD using ChemE. So they're actually using this ChemE. In this way, the ChemE has contributed to the expansion of the users and the user cases. use cases, the cloud service that can be used for everything, from quick quantum algorithm experience to the full-scale research. And at the end, I would like to discuss about the research community expansion. And coming in Japan, we host the consortium, which is called QPAC, and material and also chemical manufacturers, and over the 50 companies are the members. And QPAC is a community of researchers working at the forefront of the material development, aiming to be the first in the world to discover the potential for practical applications of quantum computers. Although the program was initially started in Japan, it began to expand overseas, and there's the event and the lectures and the follow-up seminars. And at the end, right-hand side, and there's a use case research, and that is one of the contents for the lab. And this is the use case discovery with Cambly. And for example, the team actually tried a reaction path search, and spin schedule is changed, and there's the reactions with the BQE simulation calculation that has been found. And on the right-hand side, this is about the periodic materials and the Kanno used, and that hydrogen chain transitions successfully reproduced. That was one of the example. Furthermore, from the many area, we would like to gather the knowledge from the many research area, and especially focusing on that chemical calculation hackathons has hosted this year, and 181 the people has applied for it, and the finally the 10 has been selected. And in the quantum chemistry division, the students were asked to create the demonstrations of the quantum chemistry of academic and industrial importance using quantum algorithm. And the quantum information division, the students were asked to find the basis energy of the given molecule as accurately as possible using the given number of the quantum circuit runs to that maximum extent possible. The paper is currently under preparations, and try to come up with the accurate the figures. And those are the problems. And the second problem is to calculate the ground state, the energy of the molecule with the circuit execution of the dense shot as an accurate possible. And they are preparing for the papers. So in this way, the quantum, not just a quantum area, but we are trying to gather the knowledge from the variety of the areas, and we would like to focus on this in the future as well. And from the three aspects I have discussed about our companies, and BKE is going to be expanded in the research and try to solve that issue related to that, or maybe the different algorithm, and that is going to be probably another possibility, but we would like to continue to research. And in terms of the cloud service, and we will provide that algorithm through the cloud, and we would like to expand the users and use case, and we would like to continue to do so in the future as well. And at the same time, at the QPAC, and this is a research community, and I try to expand the ecosystem, and we would like to use the knowledge from the other areas, and we would like to increase the use case and increase the algorithms, and through this as much as possible, hopefully we can come up with the commercialization of these technologies. And there's a booth, so please come to our booth if you have any questions. Thank you very much for listening.